Welcome back to Having Fun Repairs. This is Sean. Today on my bench I've got this little nightlight style toy that my youngest son got for Christmas. And it's got a minor repair that's needed to it. The boys were playing in their bedroom and somehow ended up either landing on top of this or this fell off the dresser and pushed in the bowl. But essentially what occurs is this rotates, and then you either have a white LED that illuminates and there are images stamped through this dark plastic, kind of lighter images to allow light through where you don't see this black paint, that allows the light to shine and the images move around the bedroom. There's also secondary function for a color changing LEDs. So instead of white light, you have different colors you can do. I'll tell you what, I'll show it to you real quick. Let me dim the lights, or kill the lights in my office, and then we can see it. Okay, kill the overhead lights. Here goes the white light as mentioned. It's tied to button A, on and off. Button B allows you to cycle through colors. You got blue, green, red, a blue and green, a green and red, a blue and red. You have all three colors, and then C actually causes it to rotate, which I think is pretty cool. And what I'll do after we repair this is I'll get a little bit of footage using my cell phone to show what it looks like against the wall. But really the repair is nothing special, if I'm being honest. Oh, last one cycles through all three. It's got a strobing effect. But again, the repair is, let me turn the light back on. So watch your eyes. In 3, 2, 1. There we go. The repair is nothing special per se. We just need to be able to take this outer shell off, and should be able to form this back to where it needs to be. But what I'm actually interested in is the components on the inside, and how this operates. So without further ado, let's go ahead and start taking this apart. Alright, got it fully disassembled, and I went ahead and popped this back out. Suppose I could have just taken this portion off and called it a day, but like I said, I'm more interested in what's going on here. Now, as far as the mechanics are concerned, you essentially are driving a motor with the press of a button. This piece is clipped into the base here, and then this piece slides on. You can see these locks like so, and then that twists. Now this center piece, once it's clipped in, because it is screwed into the base, this becomes non-rotationary. It just sits in the same place as this turns. And what causes this entire piece right here to turn is this gear we have on the end of our motor. And it, you can see the teeth on there. It butt rests up against these teeth here, and it obviously causes it to spin around. So it's a pretty heavy duty motor. It's covered in a bit of grease, but nothing too special with the case. Now, what I'm going to do off camera is do up a diagram, and then to make this video interesting, we will try to determine what type of IC we have right here. After I've done up the diagram, we'll make use of my power supply, my bench power supply, and my oscilloscope to kind of poke around at these different pins coming off this IC to determine what states get changed when for driving our other components, such as this white LED. They're clearly marked green, red, blue, and then our motor sitting over here. So not a whole lot of components on here, but this is a good practice, probably a good practice for anybody who's trying to reverse engineer something, to not just have it drawn out on paper. If you want to determine what type of IC we have, and there are no markings on this IC whatsoever, if that's in focus. Should be in focus now. But we at least know that it is 1, 2, 3, 4, 5, 6, 7, 14 pins. So that's something to go off on. Pin 1 being right here in the bottom right hand corner. Again, it could be oriented in any fashion on any type of IC literature. But yeah, let me reverse engineer this real quick, and then we'll go through the process of applying voltage and pushing different buttons to see what comes out of the IC to make a good determination of, hopefully, find out what exactly this component is. Well, ladies and gents, I have sunk quite a few hours into this thing, let me tell you. Almost 2 days so far, off and on, back and forth. Essentially, grab my note cards here. I went through several revisions of trying to write my own diagram for this. that one. Moved along to that, made a mistake. Then finally got this one and realized some things just didn't make sense with how stuff was oriented. And then moved to that one, which I liked, which I will go over here in a minute, as well as taking the time to probe each pin on U1, our integrated circuit, right here on this PCB. Then basically write a truth table for all of our inputs, which we will also go over, as well as what I discovered and what I couldn't find. So why don't we get into that a little bit? Okay, this is essentially what we have. Switches I labeled switch Charlie Bravo Alpha, no different than it is on the device. We have our battery connect here, USB to little small DC pin, whatever you would call it, terminal input here. The main plug going from the switchboard to your main board over here, which I've affectionately titled PI1 for on the switch, and then PIB for on the main board. We have a 1 nanofarad decoupling capacitor between our voltage rail. Our 4 LEDs, green, blue, red, and white. U1, which is our which is a microcontroller of sorts. Our motor, a transistor, NPN, and a 4.7 kilo ohm resistor. Okay, now primarily what we're looking at here is if we were to operate off of 4.5 volts battery power, so we can see the path in which current flows. Now I included the ground going to the transistor as well as the positive rail going to the other side of the of our motor, but at this point this transistor is not biased, so the motor is not on. These are just paths, but well, we can follow the current path through here. Oddly enough, I do not see a diode here for reverse battery protection. So I think that's pretty interesting, especially when we get to looking at our next input. So we could use a wall wart going from USB to a DC connectorized pin, in which case once that pin is inserted to the device, you see this little latch down here, it opens up. So we no longer have a path of current to flow between here, which is good. But I question, what if you install these batteries backwards? That could be an issue. And what if you let the batteries in with this in? I mean, is that going to be an issue? Because we're on 4.5 volts here and 5 volts here. Or the potential for 4.5 here and definitively 5 volts here. Now, if this happened to short out during that time, I mean, you've got basically 10 volts coming to the board. Or maybe because this is the path of least resistance, you blow up your batteries. So to me, I would have liked to seen a diode here to afford us some reverse battery protection. Now we can move on to our switches. We'll start out with the white LED control. Now, when I mention high, I want you to understand those highs are at the reference of our input voltage. So if we're on the wall wart here, we're essentially providing 5 volts in to pins 4 and 7. 7 I'll talk about more towards the end of our slide, because it added a layer of complication in which I also pulled that pin up to test things. essentially, you know, a high would be 5 volts here. So under nominal conditions, all your switches are going to have a high. So everything going to pins 9, 8, 9, and 10 will be high. Pin 11 will always be a ground. Pins 7 and 4 will always be high. And then our output devices are nominally high too, with the exception of our motor, which we'll see here in a second. But we'll just go from one output to the next looking at it. So again, under nominal conditions, we have a high, or 5 volts, feed into pin 8, and a high out to the cathode of our white LED. Well, because we have 5 volts on the cathode and 5 volts on the anode, no current is coming through this LED. It's essentially shut off. But the minute that we depress switch A, we trigger that high level to a low. Now this is an instantaneous trigger because this button does not stay in the depressed state once you release it. Okay. But anyways, that trigger goes low for the duration that you hold it down, and now we get a low at pin 8. And then you release the button, we go back high to up to pin 8. But because that trigger was input, pin 1 goes low, and now we have a path for current, and our white LED illuminates. Then we depress the button again to create another trigger. And over to pin 8 we see a low. And that essentially resets our circuit for us, with the output now going high and our LED turning off. Now let's look at the motor control. This one's a bit different. Nominally, we have a high coming to switch C, or Charlie, to pin 10, and a low out of pin 2, feeding into our 4.7 k ohm resistor. We trigger switch C, which presents us a low, to pin 10, and when pin 10 senses that low, it in turn switches the output to a high. We feed that 5 volts through this 4.7 k ohm resistor and get a voltage drop, getting us to about a volt, which in turn biases this NPN. And now we have a path for current, and our motor turns on. And it will stay in this state till we depress the button again to create a low trigger to pin 10, and then everything is back to its nominal condition. High at pin 10, low out of pin 2. Now for something a bit more complicated, let's look at our RGB circuit. Actually, before we do that, both the motor control and this white LED with those triggers remind me of a Bistable multi-vibrator. For those of you who want to know more, I suggest you look it up. But even on my channel, that icon that I have for my channel, that's an Astable multi-vibrator. But a Bistable is essentially affords you the ability to switch on and off an output. So there's always a steady state, but it's triggered or voltage controlled. The output is, at least. Alright, moving on now. RGB control. This is where things get a bit interesting. Nominally, like always, we're going to have a high to pin 9. And for all intents and purposes, instead of just showing every button to press, I'm just going to show a trigger on our diagram and the corresponding output. The first time we trigger it, that's that low to high, when that button's pressed down and then released. We trigger a low to high going to pin 9, and then it outputs a low to our blue LED, and now we have a path for current to flow. Then during our second trigger, it shuts everything back off, low to high again at pin 9, and our blue LED goes back high. No more current flow. So that's trigger 1 and 2. Trigger 3, we create that trigger here at pin 9 again, but this time we're switching on our green diode because the cathode is going to see that low, and now we have a path for current. And then with trigger 4, we reset it back to its nominal state. Trigger 5, we now present a low to our red LED, to the cathode of our red LED, and so it is now on. In trigger 6, we shut everything back off. Under trigger 7, we turn on our green and blue LED, presenting a load to the cathodes of both of those. In trigger 8, we shut everything back off again. Trigger 9, we present a load to the green and red LED. And trigger 10, we shut everything back off again. Trigger 11, we present a load to the cathode of our blue and red LED. And trigger 12, we shut off everything again. Man, there's a lot of triggering. And we get to trigger 13, and under trigger 13, we present a load to all 3 of our LEDs. So again, a load presented to the cathode, positive is biased at the anode, or the anode is biased by the positive, current can flow, these LEDs turn on. And then trigger 14, we shut everything back off and turn everything back to its nominal state. And then here comes something unique. During trigger 15, we actually have, or I should say actually create, a PWM signal of basically 1.93 kHz presented to all 3 of our LEDs, but each one of those pulse width modulated signals are out of phase of each other. So the LEDs appear like they glow in and out or flash. As a matter of fact, while I was scoping things out with my oscilloscope, you can kind of see each of those pulse width modulated signals here. Again, the oscilloscope showed a frequency of 1.93 kHz, but you can see every time we are presenting a low, that is the period in which the LED is illuminated. And as you look at this, the highs as well are out of phase. Basically our square wave that we develop. So there will be a period in time in which green, blue, and red are potentially on at the same time, but you can see that they kind of fade in and out at different, out of phase from one another. I would say they phase in and out at the same rate or period, but they're all out of phase. So it's almost like the LEDs kind of illuminate and they're glowing and then fade out. It's not, even though this is a square wave, it doesn't appear like an immediate shut off. So I believe that voltage is slightly ramped up and ramped down. But then trigger 16, we turn everything back off again. So hopefully that made sense to you. And the last thing I wanted to mention, because I briefly brought it up, was pin 7. I wanted to know if I lifted the pin here at pin 7, will the device still operate, or is this a pin that needs to be inverted to create a low out of pin 2 instead of the normal high? And essentially, when I lifted the pin, the entire device functioned as it should with no change whatsoever. So that got me to thinking, well, what is U1? And then the hours, and literal hours I spent scouring the internet. Let me show you a few things. All right. So the best I could determine is we have some kind of comparator circuit with some additional functions. Now, when you're trying to determine what type of IC you have, you should start out with the form factor, such as we know there's 14 pins on this. It is most likely a small outline integrated circuit, so SOIC, or more than likely small outline package, or SOP. So you're looking for a SOIC 14 or SOP 14 package size. Most likely I think this one is an SOP 14. Could be wrong, but at least that's two places where we can start, right? And when I'm looking at this, I'm trying to get a pin for pin, right? So I go to like Mauser or DigiKey, and you're going to go to integrated circuits, and you're just going to start looking for some type of controller type IC in the SOP 14 or SOIC 14 package size. And you'll just start shifting through things, such as this one right here, which is obviously not the right thing. What was this? This was a 4-bit binary ripple counter. But, you know, that's just kind of where I started my search. Obviously, our VCC and our ground are on the incorrect pins because we're looking for pin 4 will be our VCC in. Now, remember I mentioned it's tied to pin 7. I'll explain to you why I think that is a little bit later on. And then pin 11 is ground, so essentially that's what we're looking for. And then most likely this is probably a quad amp or quad comparator type circuit with some additional functions. So for here, again, not the right, well, we got the voltage 16 and 8, so our VDD and our VSS, that wouldn't work. But we're starting to get a nice comparator circuit here. What is this? Quad RS latches, because essentially you're latching the circuit. So basically, at the press of a button, you present one trigger for an output, and then you press the button again, and it triggers the device again and shuts off that output. That led me into looking for some more, and I finally found one here that was this, a dual JK flip-flop. So again, a comparator type circuit or flip-flop. If you remember me mentioning a Bistable, a multi-vibrator in general is also kind of termed a flip-flop, just like a 555 timer. Highly recommend you looking them up, because you really wouldn't have a whole lot of logic circuits or computer timing without flip-flops, especially from the well, 80s and 90s, I would presume, maybe earlier than 80s too. Most definitely earlier than 80s. Early computing technology, we'll put it that way. But just how important having a bistable is. More like the Astable that you see in the picture on my YouTube. It does not have a solid state output. It's continuous, the output shift from one to the other. And they're primarily used, you can create a basically an oscillator with them, which has a wide range of applications depending on the frequency developed by that oscillation. But again, you know, getting back to this, we see that the voltage, our VCC in and our ground is correct. But if you're deciphering the pins, right, we know pin 1 is an output and pin 2 is an output. But on this one, what was that? Pin 1, pin 2, we're just looking at 1 CP. This looks like what I used to know what that overhead hanging mean. Not 1 CP, not 1 R or something. I think those are the inverted sides, but we'll see here in a minute. 1 CP clock input, high to low, 2 CP. Oh, that's obviously not what we're looking for. Anyways, finally found this guy. What is this? Quadruple 2 input positive NOR gates. Right. Again, we have the oscillator must be built into the IC that we currently have. That is the only way I can explain how you develop a 1.93 kHz pulse width modulated signal to cause your RGBs to flashing, which you essentially just wouldn't get with a bistable or traditional comparator circuit. I don't believe. Again, this guy, you know, 14 and 7, not even close. So eventually, I first looked up. Once I determined what the frequency was, I looked up SOP 14 1.9 kHz IC chips, and got some information off of Google about that. And then I looked up the 2 kHz ones, and that gave me quite a bit more information, things to go off on. And when I tell you hours spent on trying to find the 14 pin IC we have on this device, I mean literally hours, probably about 4 or 5 hours this morning, and probably about another 4 or 5 hours yesterday. I mean, too many hours. But let me pull up what those two things got me. Okay, when I started a search on one with keyword 1.9 kHz, eventually one of the first pictures I was shown that looked like a SOIC 14, actually, yeah, it was. Form factor was this guy right here, but again, our voltage in and ground are not on the correct pins, and this is a quad 2 input and gate. So we're getting closer and closer, I think. We do have a functional table here. Of course, we just made our own. But with a quad input, that means that we at least have 4 outputs, and we have a white output, an RGB output, and a motor control output, plus 1 output that's not being used. Moving on before I get into that, then you know, still looking at different 1.9 kHz ones, stumbled across this 74HC T08 quad 2 input and gate, but again, our voltage and ground weren't on the correct pins. I think this was the last one I was looking up for that 1.9 kHz. And in the old Google box as a keyword to try to find the device we were looking at. It's an SO14 package profile, and obviously probably not going to be our size at all. But you know, pin out not good either. So then I started looking at the 2 kHz ones, and I stumbled across the 74 VHC U04 hex inverter. And again, it's a comparator circuit essentially, but you know, our voltage input and ground are, again, not on the correct pins. And looking some more. Let me see if I can make this guy a wee bit smaller so I can get more on the page. Yeah, let's zoom out. That's probably better. There we go there. Precision CMOS quad op amp LCM 6084. And I was like, man, we're almost spot on here. We got the positive voltage into pin 4 and our ground into pin 11. But here's the deal. Pin 1 and pin 2 are both in outputs. This has a inverting input and a non-inverting input, with our output being on pin 1. So this would not be the right device either, but we've definitely gotten closer. So, you know, maybe there's a one-off with this one right here, in which our inputs are over on this side, and then our outputs are effectively over here for the most part. Or actually, I take that back. Our inputs are over here on pins 8, 9, and 10, and then our outputs are essentially down this way at 11, 13, 14, and 1 and 2 and 3, which is where I believe they are. So, and then inputs over here as well. But well, that eventually led me to this TL074 low noise JFET quad operational amplifier. Again, our pin outs voltage and in and VCC are ground out, that is correct, but yeah, again, the other pins just, yeah, it's not going to work. And then lo and behold, I got somewhat the closest yet, digging through antiquated parts. This one, a Mitsubishi Electric Semiconductor quad comparator M5234P, in which case I use this web page here to look at all the Mitsubishi Electric semiconductors, and what you know, we finally have our input power and our ground are not on the right pins anymore. They're on 3 and 12 instead of 4 and 11. But our outputs are staged at the right pins in this case. Output 1, let's see, inverting input 3, inverting input, non-inverting input 1's pin 4 and 5 here. But our outputs being lower on, or I guess higher per se, if we're looking at pin 1 through pin 14 on our IC. But, you know, this is starting to make sense, and I kind of think that there is some form of alternate configuration of this, wherein pins 4 and 5 are our supply and our ground, and then the inverting pins here at 4 and 11 are probably shifted down one to 3 and 12. However, 12 was an output for us, so again, we've definitely gotten closer, but just not spot on. And then I think this last one I pulled up was LM292DR. And we can go to the data sheet here and guarantee you it's not going to be it either. Let's let it load. And can we zoom in? No, this isn't even the right form factor. This is a TS-SOP. It looks more like definitely the dimensions just off of this. And then our outputs are not correct at all. So, but if you're into trying to find an IC, I mean, that's kind of the crux of the situation you're in. When you're dealing with something as complex as this, you know, you're talking about thousands upon thousands of different versions, and then alternate versions of the different pinouts of the same device, variants per se. And yeah, for a little toy like I have up over my bench here, just kind of not worth it. Especially because, I mean, look, the main thing you need to consider is, hey, your voltage in, your voltage out. But when you're trying to take apart a device and you're probing it with your oscope, you know, there are many things that you have to consider when you're reverse engineering such as the fact that we do have an RGB LEDs, and they are sequencing. So I would want to say that we don't just have a quad operational amplifier, but it has to be programmable, which means that we will have some, not just triggers coming in for our op amps, but there would have to be some kind of counter, I would think, built into this, because just with what was it, switch B, which controlled our RGB, I mean, we had essentially 16 different triggers that all created a different change in state for our red, green, and blue LEDs. So there has to be some kind of counter in it, as well as some kind of 555 or Astable multi-vibrator, probably 2 timers total, with maybe one output of one channel not being used at all, that is why pin 7 has a 5 volts tied to it. So that way the output of one of the timers is essentially not going into oscillation, because you remove that and it doesn't affect the device. But again, you know, there would be more inside that IC than just what is right here, which kind of then led me over to discovering this MY9931 3-channel constant LED driver with cascading DMX 512 protocol. But anyways, we can kind of look at the block diagram for it, and you see that you have a current setting going into 3 outputs that will drive 3 separate colored LEDs. It looks like we have our decoder right here, built-in oscillator, and 80 APDM or PWM generator, 14-bit generator sitting here, as well as you know, kind of like an input for our comparator circuits that offer us either a positive or a low out, although I'm not sure this one necessarily just flip-flops per se with one input. Maybe it's 2 different inputs to get 2 different outputs, which kind of, you know, reminds me a bit of what we got going over here between our, what was it, channel A and channel, or switch A and switch C, which controlled pin 1 and pin 2 to the output of our motor, with channel C being a sole input. Maybe that's the mode selector for here, but in either case, you know, not the exact same pin configuration for this guy as our U1 over here, and not the right size either, as this is a SOP 16, but they did have on their website a SOP 14 configuration as well, which is definitely even more closer. But again, the bulk of our inputs and outputs are over on the left side, minus 2 outputs down here at the bottom that's constant, with our ground and our voltage being swapped here to pins 11 and 4. But sorry, I got this backwards. I need to turn inputs, main inputs and outputs over here. But either way, you see what I'm saying here. We've definitely gotten a lot closer, but for the life of me, I can't find one online that's an exact pin for pin comparison. I'm kind of willing to believe that maybe we could substitute this U1 for this guy here anyways, wherein you just take the top of the IC and mount it upside down onto the board, and then you'd have to solder individual wires from the pads to their respective pins. No different than basically what you get with a cob or chip on board, or blob chip, if you will. But that could be one workaround if we couldn't find the necessarily pin for pin replacement, but something very like with what we're looking for on this PCB. Which now brings us back to the start of this video and why I originally got this device from my son. and boom. Look, no longer dented. Now you did see me push it out, but probably in the shortcut when I was taking this apart. But there were basically, you could tell where it had been bent pretty badly because there were creases in the plastic, as well as a couple indentations that I couldn't really get to flex outward. So what I did, and I'll throw a picture somewhere up here on screen. Where's my, yeah, somewhere on one of these corners, something another. But what I did is I filled up a pot with some water and got the water to heat up, and then put this face down into the water and slightly submerged it so that way it could kind of, I didn't hold it in the water for too long, just a few seconds. Took it out, took a look at it, looked better, did it 1 or 2 more times, but eventually got the creases out, and you know, it's looking a lot better, minus the dust and dirt that's collected up on it now. But yeah, I guess it's time to put the entire thing back together and close out the video. Well, there we have it, folks. White working, rotating, blue. What is that? Green, red, blue, green, red, green, blue, red. All on. Now they kind of fade in and out. Looks better with the lights out, to be honest. I think I said I would record a piece here of it going through the office. Let me pause for a second and do that. Ooh, the lights. They're shiny. Anyways, if you found this video entertaining, and especially discussion on reverse engineering and building your truth tables and what you have to look at when it comes to finding a form fit function replacement for an unmarked IC on the board. Now, I will say some integrated circuits are a lot more easier, quote unquote, to find a suitable sub for, but because of the layers of complication and of this IC, I just, you know, after the hours I put into it, I decided enough is enough. But anyways, please consider subscribing to this channel if you're new. Thumbs up if you like the video. If you've got electronics that you're in need of repair, by all means, you can send them in to me. My business site is in the Google site, link in the description, as well as I'm now offering some exclusive videos and communications and open service on Patreon, over on Patreon, where I'm teaching TMDE and electronics principles and fundamentals of electronics engineering. By all means, if it's worthy of your time, please go there and become a member. Doesn't cost too much. Nothing more than a good cup of coffee, unless you want to go to the higher tier. But anyways, thank you for watching. Take care and goodbye.
Mark?